are going to do the physics of diving. They wear a wetsuit. And it's kind of important what the material of the wetsuit is made to make sure that your temperature stays warm. And we're going to talk about thermal conductivity. So a small thing to say is the thermal conductivity of water, is higher than air. Now, in layman terms, what does the conductivity of water mean, chat? What does that mean? Hi, Frederick, welcome in. Interesting subject. I'm here, of course, because Imonia told me to. Well, I'm glad Emo's sending people over here. We're not doing a charity stream today. Our all the incentives and bullying for the donos will be done tomorrow during our whole physics session. So tomorrow we're doing physics all day. We're doing Doppler effect, which we've done before. Then we'll do photoelectric effect, which would be fun. Who bullies? How quickly the water equalizes the temperature. Very fancy wording there, Zir. You're not wrong. Just said. Tofu bullies us. That's not true, Spooky, and you know it. I'm the receiver of the abuse in this channel, and we know that. I ended up keeping some aside to bully you with donuts. Ah, thank you, Preserve. I appreciate that. I know you've donated a huge amount though, Preserve. You, Baltrazi, Herder, Tarek. I saw so many usernames already donating on all, because I've been watching all the streams. So I already saw so many friends donate. You guys are amazing. It's the quantity of energy transferred by the water over time. Quantity of energy transferred by the water. That's a good definition. By the equation, that's a good definition. Before it is breathed. Nice. Hi, Dr. Roo. I confirm Toofs does not bully us. On the side note, I'm totally not reading from a prepared card. So, there are 3 ways that heat gets transferred in life. Heat transfers in 3 ways. One of those ways is conduction. Another way is convection. And what's the 3rd way, guys? A 3. Spooky, behave. I like how I'm streaming in the evenings now. I see you a lot more. I see you a lot more in the chat these days now. Radiation. Well done, chat. Radiation. So we've dealt a lot with radiation back in the day. Hi, Sideways. A nice blankie. Hi, Rogue. How you doing? Hello, Witar. Sorry, I'm burping. I'm drinking Coca-Cola. Well done. So, what is heat transfer by conduction? Does anyone know? Anyone want to wave their hand in the chat to tell me? Class is in session. It is, Sideways. We're learning about heat conduction of wetsuits, or like, you know, the diving suits that divers use when they dive deep down and it's cold. I have Dave the Diver music playing in the background in case anyone's wondering what the music is. Conduction through materials. Okay, that's good. Mass stays still and energy flows through it. So basically, by touching each other. Very good, very good. Everyone said all the right answers. Even though Rogue, Chocolate Mint, and Zir all said different things, they're all right. Just combine everything what they say. Molecules, especially in solid objects, are in contact together, right? Let's say you have a metal rod. All the atoms in a metal rod are in contact with each other. And when we say heat transfers by conduction, it means that this atom vibrates. It's having a rave, right? As soon as it gets energy, heat energy, it's having a rave, it's partying, it's dancing, and it starts to vibrate. And because it's squished beside another object, it starts to bump off that object and give some of its energy to that molecule. That molecule starts getting happy and excited as well, and that vibrates. And that is how heat transfers. So you guys know this instinctually. I know you know this instinctually. When you cook, okay? Have any of you guys like picked up a cooking pot on the stove and you notice that the metal handles are freaking hot AF while your wooden spoon that you use to stir is completely okay? Have you noticed that? Do you know what those words we use for materials that are good conductors of heat and bad conductors of heat? A heat sink. Welcome in, Detroit. They're all getting jiggy. Yeah, they all dancing. They be dancing. Insulators equals bad. What? So they're bad conductors, yes, but it doesn't mean necessarily a bad thing. For example, you want your house to be insulated, right? A superconductor is something different. Conductors, yes. Is that the Brownian vibration or is that different? No, Brownian, are you talking about Brownian motion? That's different. Or is it Brownian Einsteinian motion? Or Einstein-Brownian motion? How does that work again? I forget. No, that's not what we're talking about. Another thing that heat transfers is by convection. So convection is interesting. I'm actually going to spend a bit of time on this because I feel like I studied convection for years and none of my teachers spelled it out for me, and it really is actually so much more common sense. In gases and liquids, let's say you have a beaker of water, okay, this is water, and you heat it up, okay? To pretend that's fire. The molecules at the bottom are going to get hot. What happens to hot air? What do they always say about smoke, about fires? What happens to hot air? And I say air, and I know I'm talking about liquids, but liquids and air behave very similarly, so we're just going to treat them as the same for now. Rises. Hot air rises. We learned this from kids, right? When we're very, very young. It rises. Why does hot air rise? Why? I'm not trying to be a dick here, by the way. Expands, less dense. Less dense. Hot air expands. It means that it's that molecule now is taking up more space than it did. So back in the days, density is equal to mass over volume. So if the volume of your molecule has increased, then the density is going to have to decrease. An inverse relationship there between volume and density. And so hot air is less dense and will rise. Does that make sense? Sometimes, I don't know why this was not spelled out a little bit more obviously for us. It was a bit embarrassing how long it took me to actually realize this concept. But we're here now. Another way heat conducts is radiation. It's a wave. It's so simple as well, Sir Swampbutt. It's a lot more instinctual and a lot more comfortable, to cover it that way. Another form is heat, is radiation. Now, what is a good example, chat, of something that emits heat in a form of radiation? So the individual molecules expand, exactly. At a very fundamental level, that's what's happening. Sun. A sun is a perfect example. Farts, oh, for fuck's sakes, Grim. Some days you're on a roll, you're so good, and then there are days where I need to lock you in a dungeon. The sun is a perfect example. Why doesn't the sun radiate heat or emit heat by conduction or convection? Why aren't we receiving the heat from the sun using conduction, convection? Lightning bolts. Also hi. Hello, Halation. Because of space, exactly. There is no molecules in space for molecules to bounce off each other to get to us. So the only way the sun can radiate its heat to us or get its heat to us is via radiation. So that is why it's a great example. The radiation is actually infrared photons. It is, yes. So heat usually emits an infrared. That's what heat tends to be, if that makes sense. Tends to be. But there's like dust and stuff. I mean, truth be told, like it's a thing that it can radiate in multiple ways. Most things radiate in all three ways. Black body radiation, the wavelength. Yes, we should do a topic on black body radiation. It's a really cool concept. I love that whole area of science and physics. So good. You can be very locally heated by high energy particles. Now that we know all three forms, it is time to talk about suits. I'm going to talk about a super suit. What, out of all those three forms of radiation, how do you fuck's sakes. Out of all those three forms of heat transfer, which one is the one that the temperature of the water goes through the wetsuit and goes through the human? Which one are we most worried about, chat? Of all these three. Conduction, convection, or radiation? Which one do you think is going to be the one we think about? Conduction. Well done. Well done. Because like that's kind of a trick question, because you hear it and you're like, water. Oh, we just studied that it's fluids that emit heat via conduction or move around and transfer heat this way. But we're talking about the surface layer of the wetsuit. It's water in contact with the wetsuit, in contact with the human. Or the lab rat. It depends who you're drowning. But that's what we're kind of looking at here. Oop. So, I'm going to show you a mathematical equation. Thank you, Jay, for the diagrammatical explanation. So just to kind of derive and explain the equation a little bit to you, I'm going to give a simplified experiment here. That's the same referred to when you adjust your monitor's color temp, right? The color that a black body at selected temp would radiate. Oh, I actually don't know that. I have never thought about it that way, Halation. It doesn't sound that wrong to me, but I don't know. You have to be careful about black body radiation because it's not real. We talk about it all the time. It's kind of like the ideal gas law, in case anyone doesn't know. It's a perfect condition discussion, but it's approximation, okay? We physicists love to approximate, so it's a thing. It's a thing, and we make it a thing. So, just to discuss how we derive a conduction equation, or how we determine conduction equation. Let's say I have a block A and block B. They're made of two different materials, or they could be the same, it doesn't matter. And we have a rod connecting them, okay? And I'll set this, I'm going to be using Celsius, so if there's any American friends in the chat, I apologize. I'm going to set this to 100 Celsius and this one to 20. In which direction does the heat flow, from A to B or from B to A? Consider a spherical cow. You're not wrong, big boss. Hi, Baltarazi. I was talking about you earlier, about your huge, generous donations to the charity. You've been so excessive and so amazing. A to B, well done. I'm proud of you, lab rats. You guys are fantastic. From hot to cold. And you can learn that phrase off in your head if you want. That always goes from hot to cold. But can you think instinctually? Why does heat flow from hot to cold? Perhaps from a thermodynamic perspective, a statistical physics perspective, an entropic perspective. Do you guys have a little kind of analogy in mind as to why? Hi, Star Guitar. Hello, Blade. Welcome in, guys. To get the direction of this kind of conduction right, unlike electricity, that's true. Electricity still boggles my mind because the problem with me is that I usually visualize electricity at a fundamental level. So like, you know, V is equal to IR, and if you have like circuits in parallel or voltage in parallel or in series or whatever, I always visualize what is actually happening at a fundamental level. But then it all breaks down the minute you know that your potentials are on opposite sides. So like, oh shit. Because the excited electrons are moving faster and rubbing against the slower ones. Yeah, even molecules. But yeah, you're right. Because averaging the energy increases entropy. Because hot things get colder. Coffee. The cold atoms are lonely. Hot to cold. That's a good analogy. No, I know that you guys are like being a bit funny about it, but it's not wrong the way you're thinking about it. This is kind of how you visualize atoms and how they do and how to do things. So it's great examples that you guys are discussing. The bouncy molecules are going to be bouncing off the molecules that are not bouncing, and so they're rubbing shoulders and they're making the others warm. Another way you can think about it is like, you know, they're rubbing against each other and giving each other energy, and you know, it becomes exothermic. It's starting to sound not very consensual, so I'm gonna stop there. When I hit a stationary car with my car, the car slows down and a stationary car speeds up. There we go, that's a great analogy. Please don't crash your car though. Try to stay alive, guys. Let's not go down that analogy in class. Yeah, it's a good idea, Dr. Rue. Dr. Dove, heat transfer from hot to cold. Why does my ice make my drink cold while there is more drink than ice? If heat transfer from hot to cold, okay, why does ice make my drink cold? Oh, okay. Sorry, it took me a while to figure it out. What you're mentioning is latent heat, Jay, which is a great subject. What Jay is talking about is something called latent heat. I won't get too distracted about it, but it's a thing that happens when you're on borderline. If you have two phases, right? So if you have water and ice, what's water? It's a liquid. What's ice? What kind of physical matter is it? Plasma. Ice is a solid, well done. So you have liquid and you have solid. And so what actually ends up happening is the temperature is going to remain constant until this ice has completely converted to liquid. So, does that answer your question, Jay? It is it's not unusual, but what you're highlighting is a very specific situation where we have solid and liquid there. And this thing, latent heat, is a really, really big thing in physics and chemistry and all fields of science. It's a thing you have to think about. Wait, what? So, when you have liquid and a solid of the same material, so in this case water, and you have ice in there, it doesn't have to be the same material, I just kind of said it there. The question was, why does the drink stay cold the whole time even though, you know, the ice is melting? And so what's actually happening until that ice, that ice needs energy to change into liquid, and that excess energy, maybe that's not the best way of describing it, but anyways, your solution with the solid ice is going to remain constant temperature until the ice and the water completely mold together to be water. It's like how you can cook forever over 100 degree boiling in water without a pressure cooker. It's how you can't cook food over 100 degrees Celsius by boiling it in water. What do you mean, Fizzerb? Sorry. I set my own to 150. I don't think I understood that. Sorry for Zerp. I understand. Thanks for answering my question. If I put ice cubes in room temperature water, the water will be cooler before the water melts. Yes. So it doesn't. It will use that transfer. Wait, what did I say something wrong earlier? The heat of the water is still transferred to... Yes, it is. So we're talking about that equilibrium point, that 0 degree equilibrium point. It'll still go the other direction, but why doesn't it go the other direction is the question, I guess. Let me get the wording of latent heat definition right. Because I'm clearly going back. Heat required to convert a solid into liquid or vapor. Precious. No, yeah, no, I said it right. Damn it. Detroit, thanks a million for the sub. Really appreciate your prime. Thank you. So I would say that just in case anyone is looking for the actual wordy definition, I'll put it in the chat. Here you go. Detroit, thanks a million for your prime. Really appreciate it. The temp of the ice, not temp of the liquid. Yes. Depends from which perspective you're looking at. Is it the latent heat of water or the latent heat of ice? In this case, latent heat of ice, right? Let me think about this. 2 seconds. Let me get my brain working again. You put ice in a glass of water, the ice is going to cool down. Okay, so I think I have it in my head again. Sorry, I know this is very basic, but sometimes, you know, when we kind of use analogies and things like that. So when you're looking at an ice cube in a water, okay, this is like 20 degrees Celsius. And ice, let's say, is 0 degrees Celsius, okay? The question is basically, heat usually goes from hot to cold, right? But the question was, why is this not rising? Why is it that this temperature is dropping instead? Does that make sense? So your drink would get colder. Is that a fair statement, what I'm saying now? So we say heat transfers from hot to cold, but why is this not rising? Why is the ice still 0 degrees Celsius, and why isn't it increasing in temperature? And this is where latent heat comes in. It needs that energy to convert itself into water. Is that a clearer description? I'm sorry for my wording being bad. Hi, Kron. Hi, Chronically Clementine. Welcome in. What about the latent heat of mice? You can look up the latent heat of almost everything out there. Does the mass of the ice get reduced? The mass. Yes. So usually a weird thing happens. We talked about it earlier. When things get hot, they expand and they take up more space. Ice is weird. Water specifically is weird. It's actually the opposite. When water becomes cold, to the point that it reaches 0 degrees, it actually expands. So that's what latent heat basically means. It takes 80 calories per gram of ice to convert the ice from ice to water. Oh, you're not using calories for this. No way. No. Really? I mean, that is the unit for it, but... And more cold water. Exactly. There you go. Sorry for going on the different rant and saying it twice. I know I don't know if I misspoke, but hopefully I explained it a little bit better. Why it seems like heat is going the other way. Water is the weird exception, but it is only a super common it is, yeah. I guess less dense when freezing when made to confuse their... I know, Baltrazi, isn't it? Oh, it's awful. So in Tofu's picture, the cube should get smaller as the water temperature rises. Yes. As the water temperature rises. Decreases. Would you rather I said 330? Yes, actually. Joules, I understand joules. I don't understand calories. Anyways, we got distracted a little bit. Water temp cools. No worries, no worries. We're just backing up each other and confirming facts. Someone said, again, a joke about latent heat of mice. You can actually look up the latent heat of almost everything out there. It is really, really fun. How about the brilliance of aluminum foil wetsuits? Listen, 2 seconds. 2 seconds. Give me 2 seconds. Oh my god, Spooky, you did not look up tofu. How much is that in mega electrovolts? Okay, shit. Okay, I'm gonna get distracted. Thermal properties of tofu were determined in a temperature range from 5 to 8 degrees. 80 degrees. Oh god. Thermal conductivity and thermal measures simultaneously using dual probe. Dual probe method? Yeah, so for example in food science, I think calorie is actually kilocalorie. Is that a fair statement? What you guys say calories when you talk about food is actually scientifically a kilocalorie. The higher the temp of an object, the more energy molecules have. The more energy molecules have. Can everyone agree with that sentiment? Does this instinctually feel true to you, chat? So 150 calorie chocolate bar is actually 150,000 calories. So no good way to lose without munching ice cubes. Would it be off topic to ask why the Earth is reasonably cool when we're floating on giant oceans of lava? That's a long question, Laszlo. Welcome in. The answer to it, there's a lot of parameters as to why. There's the conduction of heat, obviously everything we're talking about, but it's also got to do with our position in space and the source of heat and the source of our most of our energy, thermal energy, comes all from the sun. Very little comes from the core, if I'm not mistaken. Now, when I get hot, I get lazy. Hi, Opinionat, welcome in. That's true. It's so interesting to see. There are humans out there that actually, like when they go out and sunbathe, they literally gain energy from the sun. You know what I mean? They are very energetic and they are just bouncing off the walls and all of that. And then there's people like me who will die in the heat, who will cook like there's no tomorrow. We call people like that weirdos. So there's two things that this is going to depend on. Heat transfer, this heat, this travel of heat from A to B. It's going to depend on the temperature. It does depend on how high the temperature is. And you guys have agreed with me that that makes sense to you. That the higher the temperature, the more energy the molecules will have. Okay. And another thing it's going to rely on, if you take my word for it, it's going to rely on how thick or how wide is thick. how thick this connection is, like if it's a really, really big thing or if it's a really short thing, or, oh sorry, not or, and how long this wire is. I'm not going to call it a wire, I'm going to call it a stick, a metal stick. Does that seem fair to you? Does that kind of feel common sense-ish? That this heat transfer between these two bodies, one at 100 degrees Celsius and 20 degrees Celsius, and I'm connecting a metal rod between them, it really depends on how thick that rod is and how long it is. It doesn't seem too scary or too out of pocket. Yeah, bigger rivers have more water flowing. That's a good analogy. If the wire is thicker, a lot more heat can transfer. Changes how quick it takes for the heat to transfer. Yep, great. Okay, so it does feel kind of instinctual already. Because the number, that's exactly it. You're increasing the amount of atoms or molecules that can vibrate against each other. The thicker the wire, the more atoms that can vibrate against each other. The thinner the wire, you know, they're more tightly squeezing in. They're now trying to get through that one door when there's a fire in the building and you're trying to squeeze out through that emergency exit. But what do you think about length though? Is longer length better, like faster for conducting heat, or is shorter length better? You put your hand on warm water and the other hand. Yes, I've seen those. Those are crazy. You're right, Chocolate. They are insane though. Shorter length better for conduction. Good job. Good job. And so, out of everything we just discussed there, everything we've just uncovered, we can derive a mathematical equation. We know that the change in heat over the change in time, this, don't panic, okay? Hi Torlak, welcome in. All this is, in case you don't know what this is, it's the rate of heat transfer. Don't panic. It's just how much heat we can transfer per unit time. We can go into it a little bit more. What is heat? The philosophical question. In the purest, most raw discussion, what is heat? Heat is a good movie. Is there actually a movie called Heat? Is it good? Haven't heard of that movie before. Heat is movement. Okay, not bad. We're getting close. Byproduct of getting closer. You're getting warm, guys. It is like energy. There we go. Well done. You guys got really close. It was good. It is energy. Yes, good movie with De Niro and... Oh, okay. I haven't heard of it. Might check it out. Al Pacino. Okay. I watched last night Face Off with Nicolas Cage. I don't know if you guys know that movie. It was terrible. I didn't like it at all. Anyways. It's energy. Heat is energy. But look at that unit then. Replace delta Q with delta E, guys. Change of energy over change of time. Ooh, we've heard of that before. What is change of energy over change of time? What's that unit? Joule per second. My workday. Evening. Hello, Evandria. Welcome in. Welcome in. Watt. Wattage. It is what? It is power. Energy per over delta T is power. So rate of heat transfer is power. I don't know. This might not be the biggest revelation in the world to you guys, but when you kind of start realizing how overlapping a lot of these units are, you can kind of conceptualize energy in the universe as a whole. So I think this is kind of a cool revelation if you think about it for a little bit. Portnow, welcome in. I have arrived. You can relax. Welcome in, Ebendriel. You are late to class though, so you're going in the bold corner today. So this symbol means directly proportional. And from our discussion, we know that it's directly proportional to the thickness of the rod, right? Of this rod here. What's a professional scientific word for thickness? Do we have a professional word for thickness, chat? More thoughts, thank you. Girth. Oh, fuck's sake. To be fair, I walked into that. No, you're actually right. It's actually diameter or girth, or it's actually right. You're not wrong, guys. I actually said it wrong. What I was actually looking for is area. So because girth is defined by shape. So to remove any misconception or misunderstanding of shape, we'll say area. Area. So it's area. So if it's a circle, it'd be pi r squared. If it was a square, it'd be length squared, basically. So it's area. It's also directly proportional to the delta t. Ooh, why did I put delta t? I said earlier, this is what I said. The higher the temperature of an object, the more energy a molecule has. But what does delta t mean in this situation? What's delta t here, chat? A girthy rod shape. Hi, Silver. How are you doing? Coming in the perfect moment. Change in temp. Okay, and what would that be? What number would that be, Zir, in this case? Like a potential difference. It is. 80. Well done. It's 80 degrees. It's the difference between the cold object in our case, which is 20, and the difference between the hot object in our case, which is 100. 100 minus 20, 80. So it'd be 80 degrees in our case. And it's inversely proportional to length. So if the area of the thing increases, we're happy. If the temperature is higher, the difference between the temperature is higher, we're happy. But the length, if that rod connection is really long, that's a negative aspect, unfortunately, for us. And so that is why it's A delta T over L. And that, team, is almost the equation. Why is this not an equation yet? What's wrong with this so far? There's one thing missing. Hi, Phantom. How are you doing today? Welcome in. What about the temperature of the connecting rod? We assume it's in equilibrium. Whatever that means. I think it's a perfect situation, so we ignore it. An equal sign. Well done, Beltrazi. There's an equal sign missing. And so what we do when we have a directly proportional relationship in physics, we put in a constant. In this case, it's the thermal conductivity of your material. We'll get to that in a second. You know what? Yeah, we'll do a calculation. The thermal conductivity constant is basically a value given to a type of material. That's really it. For example, I don't know why I always think of this example, but this is the example that comes into mind. Have you ever sat on a toilet seat? Maybe if you're a gentleman in the chat, you might not get too much practice about this, but have you ever sat on a toilet seat after someone sat on the toilet seat? How does the toilet seat feel? Hi, Corby, welcome in. Friday Street, let's go, Phantom! Bringing in the P and T emote. Ew. Damp. Why does it feel damp? Chat, what kind of toilet seats are you sitting on that it feels damp after someone uses the toilet? Oh my days. Hi, Science Fish, welcome in. You guys are coming in at the perfect moment. Okay, let's be a bit professional and scientific here. The toilet seat is warm, right? It turns out that material that the toilet seat is made up of heats up really quickly. So if someone sat down, you know, it's a good conductor of heat. Its thermal conductivity is different. Have you... I don't know why. Maybe it's because I'm a woman, right? And I go to many bathrooms out in public. But you can almost tell which toilet seat is going to be sore to sit on. Not sore, but like the sharp coldness of it. Depending on what that toilet seat is made out of. Is that something you guys feel instinctually? Like, you look at a toilet seat and you're like, oh my god, that's gonna be so cold. That's gonna be so cold. But some toilet seats are like, oh yeah, this is the jam. I don't know if you do say that, but you know. So, every type of material out there has its own thermal conductivity. Some materials conduct heat better than others. And this is also, okay, the classic examples is cooking. If you have a metal rod that you use for cooking, that's going to heat up really, really quickly. But if you have a wooden stick and you're cooking, that's pretty much an insulator. You're not going to burn your hand. That's the classical example. I do feel like you remember the toilet seat a lot better though. I think we all feel the toilet seat a bit personal. Maybe I've just been attacked by toilet seats. To be honest, that question never crossed my mind. Yeah, I think you guys just don't know what it's like to, you know, go in public a lot more on sit on toilet seats. Maybe that's just me. But yeah. Hi, Fabric. When I'm not at home, I always use a layer of toilet roll. The dreaded ceramic seat. There's metal seats, ceramic, there's like plastic. Plastic is the better one. I will remember that my teacher's weird. Do not like toilet seats that are below freezing. Ooh, that sounds amazing for Zip. So that is what K represents. Every single material out there has its own conductivity value. The higher it is, the more easily it conducts heat. The lower it is, the less it conducts heat. Hi, welcome in, Karmakar, welcome in. Tongue sticks to them. So that's exactly what thermal conductivity is. So let's do a calculation. Let's do a simple calculation, just so that we practice, so we can kind of get a bit of practice with this equation. So if a diver has a small but girthy rod, they will get cold quicker. No, the opposite. If they have a... Oh, sorry. No, you're right. Yeah, sorry. I didn't know which direction you were going. Never mind. You're right. My music stopped. I had to play it. Yay! Okay. Let's take a pane of glass. Why do we call it a pane? It's not even a pane, actually, what I want to say. It's a piece of glass. Your glass window. Okay? Look at this amazing drawing. Jay would be so proud of me. We need a toilet seat material index. To be, like, no joke, I'm pretty sure that's a legal parameter they have to put on when they sell you materials, guys. If you're building a house or building a toilet, I'm pretty... Look up the thermal conductivity of your toilet seat before you purchase it. Or buy a toilet seat cover if you have to. So let's say this glass is 3 meters tall, your window in your house, 2 meters wide. This is not proportional, clearly. And we'll say 1.4 centimeters thick. Okay. And we'll say that outside is 22 degrees Celsius and inside is 25 degrees Celsius. First of all, which way is the heat going to transfer? So this is inside the house. Is it go from inside to outside or outside to inside? A fuzzy pink toilet seat. In to out, exactly. It's going from inside to outside. It's going this way. So heat is, we're losing heat from the house. From my burping. We know that the thermal conductivity of glass, I just kind of looked up this value. I could be wrong, but it depends on what glass you get, by the way, is 0.84. I'm actually going to write it here because the units won't fit in. And we can derive the units, but you can also just trust me. Trust me, bro. 0.84 joule per second meter Celsius. I'm actually going to change that to Kelvin. I'm not trying to be a bitch about this, but it doesn't matter if I'm doing Celsius or Kelvin. Why does it not matter whether we use Celsius or Kelvin here in this equation? Same scaling. It cancels because C is equal. So it's not that necessarily C is equal to K. Just a small correction there, Phantom. Delta C is equal to delta K. Because we're dealing with the difference in temperature. 25 degrees Celsius minus 22 degrees Celsius, which is 3 Celsius. Their Kelvin equivalent is going to be the exact same. It's only... I said it linguistically. This is only... Not every single equation is like this. Not every single equation is delta T. Sometimes it is a absolute temperature. And if it's absolute, you have to use Kelvin. I say have to. There's usually adjustments for Fahrenheit and Celsius. But general rule of thumb in physics and science, use Kelvin. Even if we don't like him. So we actually have all the values here. From this diagram, we can calculate the conductivity, how much energy changes per time, the power, we'll say, of the situation. K is 0.84. What's the area of our window? Because the alpha decay will warm our butts up a bit with uranium seed. This is what happens when we mix up our classes. 6 meters squared. Well done. You chat are so smart. You guys are too smart for this stream. And delta T? What's the temperature change? Three. Well done. 80 was the other one. Sorry, I've moved on. What's the length? Y3, 25 degrees Celsius minus 22 degrees Celsius is delta T, the temperature change. So it changes from 25 degrees to 22. 0.014 meters. No? Yeah. Well done. So if anyone doesn't know, the thickness I said was 1.4 centimeters. I just converted it to meters. You shove that all in your calculator and the answer you should get is 1080 watts. I don't know if that's usually the unit that's used. You can also use joule per second when we specifically talk about heat transfer. Keeping the unit same for the win. I thought that was 28, not 25. That's okay. My writing can be a bit inconspicuous or problematic. So, we can actually use this equation. We know the thermal conductivity of certain things. Now, I said that glass, a number I pulled out of my arse, is 0.84 joules per second meter per Kelvin. Meter Kelvin, not per. Per means divide. I'm going to give you what the... I just googled this. What the thermal conductivity is of a wetsuit of a diver. 0.054 joule. And a glass does not conduct heat that easily, guys. It does not. But this is just a quick search of what the conductivity material of a wetsuit is. Okay, so we can tell now by this number that it's very, very small, right? It does not conduct heat very, very easily. Does that make sense? Is that a fair statement? Do we agree with that? Hi, Morton, welcome in. The thermal conductivity of copper is about 400 times. Yeah. Okay, so we agree with that, what I just said there, right? That the thermal conductivity of water, of a wetsuit, is super, super, super low. How does that keep you warm under the water? Because if you guys have done a wetsuit, if you guys have dove in, like, it's not that the water seeps through into your wetsuit, you know? How is that good for keeping your body from getting too cold? I need a better overlay for this part. Your body produces the heat. That is part of the answer. Well done. Okay, the wetsuit I usually wear is 4 millimeters. Oh, you can even do the calculation, Baltrazi, for this if you want. It reflects your body temp. When the teacher asks you a question, you can't help but think it's a trap. It's more like it keeps, it's keeping the water from getting warm. It's also part of the thought matrix. So there's actually a lot more conditions to it. Like someone mentioned there that it's like a second layer of skin, that things like that. But what ends up, like, the value of this, or what it's kind of portraying, is that because the water adds more surface area, the water warms up and acts like an insulating layer. But we just said that it warms up super, super slowly, Brutus. So you guys are saying the water warms up in the suit. But I just said that the thermal conductivity of the suit is super, super low. The water inside the suit heats up. Okay. I'm not being an asshole about this, by the way. I am probing you guys. I have an idea of how it works. Haven't looked this up properly. We're doing this for a bit of fun. It acts like a thermal compound. Yes, so the way I understand it is you have some water in your wetsuit. And because it's a thin layer, it's cold in the beginning, right? On the surface, but it's fine. It's a thin layer, you put your suit on and your body will heat it up really quickly. It's kind of like getting cozy in bed during winter. So when you jump into bed and you cover yourself in the blanket, it's fucking freezing in the middle of winter, isn't it? But it's so cozy because like you warm up the air and everything. And then like after 20 minutes, like if you move even an inch, you're frozen again. You have to stay back because your body has warmed up the bubble of air in your blanket. Does that make sense? It's kind of like that. That's exactly what's going on. Yep, farts warm you up. Fuck's sake, spooky. We clearly have missed you on these streams. I'm glad I switched to evening streams so you'll be here. Hi, Cora. Welcome in. Dark, thanks somebody for the follow. Hi, Yuli. Farts are definitely a cheat code there. Anyways. So you have this thin layer. And what this conduction, this low conduction of the wetsuit from the outside water does is that it takes forever for any new warm water to re-enter your body. And it goes the other way. Okay, let me show you. I'll do it diagrammatically. So the first step is you wet yourself. Not like exactly like that. But in the wetsuit, you're wet in the beginning, right? I'm just oversimplifying the wetsuit here. And there is a thin layer of water inside your wetsuit. That's your body in there. But your body has now heated up this water. It's happy. It's at 36 degrees Celsius. After a little time... Oh, shit. Sorry. Thank you for saying I'm on the wrong overlay. Appreciate it. Share board. Yep. So we have a wetsuit like this. And inside, you're all toasty and warm. Your toasty and warm body is heating up the water inside. Now, which way... and then you dive into the water. For some reason, it's a beaker of water. And it's freaking freezing, right? It's 10 degrees Celsius, let's say. Which way does the heat flow again, guys? That's a three-legged shorts. It's a top. It's a t-shirt. From hot to cold. So the low thermal conductivity is actually to slow down you losing this heat. Does that make sense? For some reason, when I first thought about diver suits, I was just sitting and thinking about it. I thought it was all about keeping the heat trapped in. As in getting the heat in. That part is actually taken care of immediately. The whole process is to stop the heat from coming out. They almost mean the same thing technically, but in my head it's a bit of a different analogy. Does that make sense? What the wetsuit is doing, that low number, this low number that I talked about, is stopping a diver from losing heat when they're diving. Does that make sense a little bit now, guys? How it works? From in to out, from hot to cold. Yes. Okay. Well, one person said yes, so I consider that a win. That's a win. So that is how divers generally stay warm. Do we know the average thickness of a suit? We can look it up. We can measure it. Someone said that they have a wetsuit there in front of them. What's really cool about this, if you as a physicist, if you as a person who's a physics enthusiast, this came to me logically. If that makes sense. When you just practice these kind of things, a lot of things will just click in with you in common sense. So you might guys do a calculation and you might figure it out. What is a dry suit then? I have no idea. I have no idea how a dry suit works. I'm not even sure. Is a dry suit actually dry? No sarcasm intended. Is the inside of a dry suit actually dry? I'm a diver, not a physicist, so this is cool for me to learn. Beltrazi, that is fantastic. Dry suits are dry. Then I would say it's just complete. It's the same system. It's the exact same system, except there is no water inside the suit. So again, it's about keeping the heat of your body in and slowing down the water temperature from outside. It's trying to keep it trapped inside. That's what I would say that is. Again, I'm not sure if that's exactly it. Hi, Fexter. Welcome in. How you doing? I saw you in so many chats the last few days with the Emo's charity stream. So wetsuits are like a winter coat. No, I'd say dry suit and wetsuit are the same thing, Sir Brutus. Except literally by only wordy definition. They do the exact same thing. Dry suit just does it with air, while wetsuit does it with water. Is that a fair statement? I feel like that's a fair statement, but I could be wrong. Omnifexter. That's how I understand it, yes. That's the way I understand it as well. So that was the physics of heat balances that divers have to deal with. Like a window uses air between, exactly, it's a really good insulator. Hi, Tom Gunner. I saw you earlier in the chat. I don't know if you saw me reply to you at like 5 o'clock. I happened to have Twitch open. Your body hair holds a layer of insulation. Oh, so Ebendriel, the hairier you are, the better for diving it is. A lot of windows use argon gas. Oh, I didn't know that. I didn't know. Cool. Well, I hope we learned something. I felt like I learned a lot. Like, again, I never thought about divers. I never thought about, you know, how they keep their suits warm and stuff. Didn't really cross my mind to think about it, and now I did. And yeah, I feel that little bit smarter. In case I'm gonna lurk. No worries, Fexter. Thanks a million for the lurk. Hi, Roy. How you doing today? Diving is using a gas mixture to maintain certain partial pressure. Yes, so the other part that I looked up is partial pressure as well, Lint. Welcome in. Hello.